I'm Mariangela, and my research group focuses broadly on different ways in which we can detect dark matter using either astrophysical signatures or terrestrial searches. And over the course of the next 45 minutes or so, I hope to kind of be able to show you one small subset of that, the class of dark matter that acts like waves. And I think that's why this sort of fits into the theme of these series for this spring term. So dark matter is one of the big unanswered questions in physics. And there's an incredible amount of evidence for its existence. One of the sharpest pieces of evidence comes from the motion of galaxies. So in particular, if we look at stellar gas disks in the center of any kind of large galaxy like the Milky Way or something like that, and we look at how rapidly it's rotating around, we can make a prediction just using sort of standard Newtonian physics, which sort of predicts that as you move further out to the outskirts of that disk, the galaxy should start moving more slowly. So you should start seeing the rotational velocity kind of fall off. What's actually observed, and this was first noted in groundbreaking work by Vera Rubin and Ford in the 1970s and early 1980s, was that the rotation actually doesn't fall off as Newton would predict, and instead it sort of plateaus out at a constant value. So this has very sort of visual consequences. If we just look, what does that actually mean for the rotation of the galaxy? This is what we would actually observe, and this is what Newtonian physics, Newtonian gravity would predict. So you do see the outskirts kind of rotating around much faster. And the interpretation of this is, still open for discussion in some ways. There's two possible ways we can account for this. One is we can say, well, okay, Newton must be wrong. We need to go back and redo our theory of gravity. And the second option is to say that we're not accounting for all of the mass that should be there in the galaxy, that there's actually more mass than we can see, and the presence of that additional mass is what causes the galaxy to be rotating faster. And in a comment from Vera Rubin herself in 2009, she sort of acknowledged these two possibilities, sort of shrugged her shoulders, said, sorry for causing all of this debate, don't really know what it is, but hey, it's fun to be talking about all of this. And it sure is. The talk today, I'm really going to be focusing on the second interpretation where we add more mass. The first scenario where we say we need to go back and revise Newton's laws, that so far has not actually led to a consistent model that works over all cosmological time. So that doesn't mean that may not end up being the solution at the end of the day, but at the moment, where we're seeing the evidence pointing to is really this hypothesis that we're not seeing all of the matter that's there. And I hope to kind of show you some of that evidence as well. So in this sort of way we think about it, we say, okay, well, here's actually the visible part of the galaxy, and it's surrounded by a bunch more mass that we can't see. And there's a lot of it that's there. I mean, really a lot of it. I tried to draw this to scale, but I don't think I quite achieved it. Really, the amount of mass that would be in this big halo, we call it a halo, is about 10 times more than the amount of mass that's in this disk. And actually, the sort of actual spatial extent is about 10 times as large as the visible part of the galaxy. So really, when we look at it and we think of a galaxy, we think of a rotating stellar disk, that's really just a tiny little speck, we believe, of all that's actually there. And the vast majority of that's there, we can't see at all. This hypothesis that we have these massive halos of dark matter surrounding the disks in the center of galaxies works to explain the rotation curve measurements that have been made roughly sort of galaxies that are near us and also for our own Milky Way. What we would want to ensure is that this hypothesis also holds as we look at evidence from different periods of the universe's evolution. So this is just a schematic diagram, showing how the universe evolves from the period of the Big Bang, so that's the birth of the universe initially, all the way up to the present day. So the rotation curve data that we have is really coming from sampling individual galaxies here on this end, but we want to check and ensure that as we move backwards and gather data that's coming from earlier epochs in the universe's evolution, that also upholds this picture of, and is consistent with the interpretation of the presence of this dark matter component. So there's two sets of this data that I want to highlight, really because it's quite spectacular. The first is looking at the structure of that galaxies, when we look at a whole collection of these galaxies, make across the sky. And this structure really looks like a cosmic web, so sort of think of like a spider web, but really just composed of a bunch of galaxies. And you can see the data here in blue from different surveys, blue and purple. So these are kind of different patches of the sky, and each little dot here is an individual galaxy that's observed. And then where the coloring is really dark, you have a bunch of galaxies that are all kind of clustered together. And so what really stands out in each of these panels here is that web-like structure for how the galaxies are distributed across these really large scales. And what's remarkable is that if we put into our theory of cosmological evolution the ingredient of dark matter, we can reproduce precisely that kind of web structure. So the red and pink panels here are from simulation for the same patches of sky, roughly the same patches of sky. And these simulations include in them an additional component of dark matter. And what you can see just by eye is that it does just an amazing job at kind of reproducing the same kinds of structures that we see in the data. So that's kind of a rather spectacular confirmation that this the addition of dark matter is sort of a critical ingredient to our understanding of how of the structure in the universe. If we go even further back in time, to the point where the universe was only 380,000 years old, at that point in time, hydrogen was just being formed, and that's essentially the point in time when photons and light stopped scattering and essentially just started free streaming towards us today. We can record those photons from that very, very early epoch in our universe's evolution, and this is what they look like across the whole sky. These are the coloring here is the temperature of the photons that are recorded, with red being a little bit hotter and blue being a little bit colder. And so you sort of see that there's these temperature fluctuations. There's definitely some kind of a little bit of structure across this. And this pattern that we see here, again, can be explained beautifully with this model where we add in this additional dark matter component. And so to illustrate this, what I'm showing here is essentially a summary plot of this. So what this is showing is the power on different angular scales, where this is large scales and small angular scales. And what I mean by angular scales is literally just sort of like, think of it as a small, like the size of the patch that you're considering on this sky map. So the data that we have, and this is actually pretty old data, is shown with these points with the error bars. The error bars are even a lot smaller now. This is from 2015, but Planck has had further data releases since then. And the best fit model that includes dark matter is shown in solid blue. And just to show what happens if we just take that same model and tweak it a little bit and just reduce the amount of dark matter that's in there, then the theory prediction looks like the dashed blue. So it's incredible, this data that we have from this sort of snapshot from the early universe. It really allows us to essentially do precision physics and really understand and quantify how much dark matter exists in the universe in order to be able to explain the structures that we see here from this photon data. So if we take all together all pieces of evidence, of which I've only highlighted some, not all, this is essentially everything we know about dark matter, which may not seem like a lot, but it's what we have to work with. We know that about 84% of all of the matter that exists is dark, which means that 15% is the matter that we all know and love. So standard periodic table of stuff, that's only 15%. The rest is this 84% that we really kind of have no idea what it is. What we do know about it is that it's non-relativistic, so it's not moving terribly fast, and it's weakly interacting. And by weakly interacting, I just mean we haven't been able to see it, so it can't interact with light. And so we can make statements like that, and that tells us that if it had been interacting more strongly, we would have been able to detect it, and we haven't yet, other than through gravity. Now we can ask, well, is there any other particle that we already know exists that can explain this? And the answer is no. So we can go to our standard model of particle physics, which lists all the fundamental particles that we know of. It's shown here. So it's, we've got our quarks, we've got our leptons, our electron, muon, tau, our neutrinos, our Higgs boson. These are essentially all the fundamental particles that explain how matter is built up in our universe, and how forces are mediate interactions between those matters. And really, the only thing here that could potentially serve as dark matter are the neutrinos, because they're essentially extraordinarily weakly interacting, and so they would sort of satisfy this requirement here. But it turns out that they can't comprise all of the dark matter. It would end up causing actually quite a few problems if they did. And so they're probably just a small fraction of the dark matter, but can't explain all of it. So that still leaves us with the big question of how do we actually extend our current model to be able to include candidates that could be this new dark matter. So what we're going to do together is essentially explore the possibility that this new particle is one that acts like a wave. And this is a really fun class of dark matter particles to consider. It leads to some really interesting effects, both on large cosmic scales as well as in experiments that we're building on Earth. And so we'll be able to kind of cover and sample a bunch of that through the examples that we'll go over for the rest of the talk. So to actually learn something and be able to say something about how can these dark matter particles be waves, and what kind of properties do those waves have, we can actually get a lot of traction by just thinking about the kinds of structures that have to exist if galaxies were to form. And so what I want to do is then just take a moment to kind of go over how galaxies evolve, because we're going to use this a lot to be able to make some statements, some pretty powerful statements about what this wave-like dark matter can be and what it can't be. So in the sort of stages of getting a galaxy that eventually ends up looking like, let's say, our Milky Way galaxy, we start very early on where there's just happens to be an overdensity of matter. In this case, it would be an overdensity of dark matter. And that overdensity of dark matter essentially then ends up exerting a gravitational pull on gas that's present. And so that gas sort of sinks down to the center. And that's essentially the birth, the sort of birth site of a new galaxy there. And then as this evolves, then sites where you have very high gas contact, very high density of gas, will turn to stars. So then you'll start getting some stars forming in the center of the galaxy. System continues evolving. You end up getting central black holes. Galaxies collide, and so they end up growing in that fashion until you end up getting systems that look like what we know of today. And in this evolution, the properties of the dark matter play an important role and can actually kind of mess things up depending on what you assume. So for example, if I were to assume that the dark matter very early on had a very long free streaming length, that would actually just sort of tend to wipe out the formation of these kinds of clumps early on. And then I no longer have places where I can, accumulate gas and form galaxies and things like that. And I can end up destroying structure in a way that I don't want to destroy it. So in order to be able to preserve this kind of galaxy evolution, we need to be careful about the assumptions that we make about the dark matter particle itself. Moreover, if we zoom into any one of those galaxies, there's actually a lot more structure there than what was illustrated just on the previous slide. So what I want us to do for a moment is just imagine we put on our dark matter goggles so we can actually see all of the structure that the dark matter forms. This is what it would look like for a Milky Way galaxy. So the sort of big circle here would be the big dark matter halo around the Milky Way. And you can see that there's a sort of obviously a big density of the dark matter near the center, and it falls off as you go to the edge of the halo. But there's also these it's peppered with all sorts of structure. Each one of these is sort of a high concentration of dark matter that's like flying around in that galaxy. And the largest of these will themselves end up having gas and maybe some stars in them. And those end up becoming what are referred to as dwarf galaxies. So these sort of small galaxies that end up orbiting around the Milky Way. The clumps that are even smaller than that may not actually have any gas or stars in them at all, and so they may just remain completely dark and just kind of continue flying around. And that we have yet to detect, but could actually be present. So this is just to show that we already have a list of these dwarf galaxies that exist in the Milky Way. These are just some of them here. And the fact that they're heavily studied because just their presence and their properties really can teach us a lot about the nature of dark matter. So that's actually what I want to do next, is kind of show how we can use the fact that these dwarf galaxies exist to make some statements about what masses the dark matter can be and whether or not it can act like a wave. And in order to make that jump, I just want to remind us of sort of a basic tenet in physics, which is wave-particle duality, where in the classical case, we think of there being essentially a degeneracy between the mass of an object and whether or not, and its wave-like nature. And we can sort of go back and forth between thinking of something as acting like a particle versus it acting like a wave. And that's really embodied in this relationship here, which relates the wavelength of a particle inversely to its momentum. So if I drive the mass of a particle really low, while keeping that velocity constant, then I can make this wavelength really large. So I can then end up having sort of macroscopic wavelengths if my particle is ultralight. And the kinds of masses that we'll be talking about this evening are going to be masses that range from about an electron volt all the way down to 10 to the minus 22 electron volts, which, if you're not familiar with those units, I can rephrase it in terms of wavelengths instead, essentially just using this relationship here, right? For any mass, I can restate things in terms of a wavelength. So we'll be talking about waves that go from wavelengths that are about the size of an ant all the way to wavelengths that are about the size of a galaxy. So that's kind of the range that we're going to be focusing on. And for perspective, here's the electromagnetic spectrum. So we're going to be talking about, our dark matter waves essentially fall from between microwave to infrared, down to radio, and way, way, way below radio in terms of a comparison to the wavelengths that we're referring to here. So there's really an incredibly wide range of lengths that we're talking about. So let's piece this all together. And say, okay, well, what we need to exist, because we observe them, are these small dwarf galaxies. So if the dark matter is going to behave like a wave, we still need it to be consistent with the fact that we observe these dwarf galaxies. So in particular, what that means is that the wavelength of the dark matter cannot be any larger than the size of the halo. If that happened, then the halo itself wouldn't exist anymore. And so that means that the smallest possible halos set a limit on the wavelength, the allowed wavelengths for dark matter. So and the smallest possible halos are going to be those dwarf galaxies. So the size of the smallest dwarf galaxy essentially sets the minimum, the maximum wavelength allowed for the dark matter. And so collating through all the data, looking at all of our dwarf galaxies, looking at their sizes, that ends up giving us a mass scale for the dark matter that says it has to be greater than 10 to the minus 22 electron volts. So these would be wave-like dark matter candidates with wavelengths that are on the order, by definition, of these small dwarf galaxy systems. And just to kind of provide a counterpoint to this, the statements that I made here are very specific to what are called classes of particles known as bosons. If we instead talk about fermions, the allowed mass range is very different. So this all comes down to essentially the Pauli exclusion principle. So if instead my dark matter was not a boson, but instead was a fermion, and I wanted to try to pack everything into this halo, I'd only be able to put one dark matter particle in any kind of unit of phase space that's allowed in that halo, in the same way that when you're packing electrons around some atom, you can only pack them in very specific ways. And so that actually changes the number of dark matter that I can squeeze into that halo. And that in turn ends up creating a very different mass range in which you can have these kinds of fermionic dark matter particles existing. So if we put this all together, here's a full sort of mass range for the dark matter. Wave-like dark matter exists here in this range here marked by the blue. For a point of comparison, this is the electron mass, and that's where a proton mass is. And particle dark matter exists in this yellow range. So we'll be focusing just on this case here, but there's a whole breadth, give a whole other talk on everything that you can do with dark matter that goes out in this range. And actually this particular spot right here is a class of dark matter that's sort of really actively being pursued experimentally and sort of very theoretically interesting, which is why I marked it off here, but it's definitely not wave-like. But we're going to build a lot of intuition for what happens when the dark matter is in this range, so very ultralight, and then with wavelengths that can be as large, at least on this end, wavelengths that are essentially as large as galactic scales. So in precisely that regime where you have these incredibly large wavelengths for your dark matter, it can lead to really beautiful signatures on the size of galaxies. So all the kind of wave phenomena that we're used to thinking about, like interference effects, constructive interference, destructive interference, all of that's going to end up playing out as galaxies form and evolve and the universe continues changing with time. And to highlight that, I'm going to show you some images from simulation. I'm going to show you by starting with a case that's not wave-like, and then as a counterpoint, show you the wave-like scenario. So this is essentially a snapshot of the cosmic web for a dark matter candidate that's not acting wave-like, so we'll refer to as cold dark matter. So you see that sort of intricate web-like structure we discussed earlier. And when we zoom in on a patch of this, you see that the dark matter ends up concentrating in these dense regions. And then areas where you have very high concentration of dark matter is where you accumulate the gas. So then if you look at the gas, it's sort of, again, concentrated where you see the dark matter being concentrated. And then high regions of gas, high density gas is where you form stars. So here's the corresponding stellar star distribution. And so if you were to make an observation of this, what you'd actually be seeing is the gas and the stars. You would never see the dark matter. But the sort of structures that you see are in those observations is predicated on how the dark matter itself had clustered. So now I'm going to show you something very similar, but where we consider the dark matter as being wave-like instead. And you can see that the structures are quite different. So here it is, that sort of the cosmic web somehow gets a little washed out. You can still sort of see it, right? There's a little bit of it there, but it's getting kind of washed out. If we zoom in on, this sort of patch up here, now for wave-like dark matter, we're not seeing as much of those sort of tight clusters. We're seeing this sort of kind of more like linear type density here. And so because the dark matter distribution is different, the corresponding gas and stellar distribution is going to change as well. And so here's what the stars would look like associated with this patch. And zooming in even more, you can actually sort of see these interference effects that are actually occurring. That's literally interference between the dark matter waves, and it shows up as these kinds of structures on the galactic scales. So this is just a really stunning kind of illustration of how changing that dark matter properties really kind of changes the observations that we make. And these are for early forming galaxies, about a gigayear into the age of the universe. So this is precisely the time range that like James Webb Telescope has sensitivity to. So they're starting to gather data for these very early forming galaxies. And one thing that's going to be very interesting is to sort of see the types of structures that they observe and understand what the implications are for the properties of the dark matter particle itself. Here's another example where the wave-like nature of dark matter ends up having implications for these dwarf galaxy-type systems. So you end up getting wave interference because the dark matter acts like a wave. So there's going to be patches where you end up getting coherent, constructive interference, other patches where you get destructive interference. And so if we look inside a halo of dark matter, you're going to end up getting regions of overdensities and underdensities having to do with where essentially all of these interference effects. And the presence of these over and underdensities has an impact on the stars that are present in those galaxies. Because when you have an overdensity that forms, it can gravitationally interact with the star and kind of kick it around and give it some extra velocity dispersion. And we can go out and observe these systems, especially the ultra-faint dwarf galaxies, which are really great places to look because they're sort of very well behaved. They have very small velocity dispersions. And compare with the expectations of how we expect those systems to have been heated up if the dark matter was wave-like in this nature. And even with sort of just current data right now, these systems have been really powerful in testing these ideas. And actually, with the current set of data, this particular scenario up here, which is sort of masses in 2 × 10⁻⁹ eV range, this one here is actually borderline excluded. This one here would be allowed, and you can sort of see by IY. In this case, the mass overdensities are going to be a lot smaller, so you're not going to be heating up the stars to the same degree as you would for this case up there. So now that we've really kind of seen what happens when we think about wave-like dark matter, especially in the range where the wavelengths are galactic scale, so like really large, and we get these sort of magnificent types of interference patterns on the scales of galaxies. What I want to do is sort of move to higher masses, which corresponds to smaller wavelengths. And as we sort of march in that direction, we end up hitting a very interesting regime. So we were here, like a lot of the pictures and simulations I was just showing you were in this regime, so very long wavelengths. So we're going to march our way this way, so wavelengths are getting smaller as the mass gets higher. And this range here is where there's a very well-motivated candidate called the QCD Axion. And it's so well-motivated and of such theoretical interest that I thought it deserved its own sort of special section in the middle of the talk to kind of explain to you what the motivation for this candidate is. The reason that the QCD Axion is so special is because it actually has the potential to answer 2 big questions in particle physics. One is it can actually explain the dark matter, so yay, that's why we're talking about it here. The second is that it can also explain another mystery, which has to do with the neutron-electron dipole moment. So let me give you some background on that second mystery. The electron dipole moment of a particle is essentially telling you something about how charge is distributed in that bound particle. So the neutron, for example, consists of one up quark and two down quarks. An up quark is roughly exactly 2/3 the electric charge, and a down quark is minus 1/3 an electric charge. And this is a sort of very simple schematic, but I think it'll convey the main ideas. When we talk about electric dipole moment, we're essentially talking about how we distribute these charges within the neutron, so how we orient the down quarks relative to the up quarks. And you could do sort of a super simple estimate just off of this kind of simple geometric picture that this electron dipole moment for the neutron should scale as follows, where theta is this separation angle here between the up quark and the two down quarks. Now, let's compare that to the measured value for the neutron EDM, which is effectively 0. There's been a lot of fantastic work in this area. Measurement is 0. There's some small systematic uncertainty in that, another small statistical uncertainty, but effectively it's 0. And so what does that mean? Well, the only way that we can get 0 here is if cosine theta up there is 1, which means that this is the orientation of the up and the down quarks in the neutron. And that's weird. For any particle physicist, as soon as you end up getting anything that makes a prediction for a number that's 0, all sorts of red flags go off because you're like, why is it 0? 0 is a special number. How am I going to explain 0? It might be indicative of there being some sort of special symmetry that's there, or maybe there's some kind of energetics kind of reason. So like maybe this minimizes the energy of the system when that angle vanishes. And it turns out that the axion is one way in which we can minimize that energy and explain that configuration of the up and the down quarks in the neutron. And it's, by analogy, it's very, very similar to how we think about bonds forming in chemistry. So when we think about bonds forming, we're thinking about how two atoms can end up arranging themselves such that they end up minimizing the potential energy felt by the electrons in that they share. And so the actual sort of stable state is going to be the one that minimizes that energy. So for example, carbon dioxide is sort of linear molecule like that. And that linearity is essentially set by the fact that the bonds that result are the ones that end up minimizing the energy of the system. And it so happens that that means that the molecule itself is linear and also, as a result, has no electron dipole moment. So by that same analogy, the way we think about the neutron EDM is to say that we have, we introduce a new particle, we call it the axion, and we say that the axion can interact with quarks and gluons in such a way that it sets a potential energy. And when we minimize that potential energy, we essentially choose the special value of theta of 0, which is what we actually observe. And so the more detailed picture is a little bit more involved in the cartoon I showed you. I'll just flash it quickly. So we start with this sort of potential energy that looks like this. So this is very early in the universe's evolution. After a certain point of time, that symmetry is broken. And at that point, the axion is essentially associated with the valley of this sort of wine bottle shape that you end up getting. And it can take any, so the theta that we think about is essentially any value along the valley of that wine bottle. So at this point in time, any value of theta is allowed. But as temperature continues to decrease in the universe, then you reach a point where the axion actually gets a mass. That wine bottle tilts just a little bit, so you get a tilting of the potential energy, and where that axion particle ends up settling is right at 0, which ends up explaining the 0 that ends up explaining the neutron EDM. So there are a variety of ways in which we can do this in the universe's evolution. I'm going to skip some of these images, and I'll just kind of summarize it here. So just to kind of put this in perspective in terms of the broader picture of how our universe evolves, here's the Big Bang. Here we are today. There's this period very early on referred to as inflation, where we have sort of this accelerated expansion. And that sort of symmetry breaking process that I described to you can either occur here, right before inflation, or here after inflation. And there's different sets of observable consequences depending on when that process happens. So one really neat thing about these QCD axions is that they end up impacting how black holes move. And so this is, it's just such a beautiful picture, I had to sort of share it. And we can get a lot of intuition from this just from a very simple mechanical analogy. So where we have a rotating cylinder, imagine with some like rough surface, so it has some like friction on it, and we throw in a ball. And if this rotating cylinder is moving faster than the ball when the ball hits it, then it can give a little energy kick to the ball so that the ball speeds up as it flies away. And that ball essentially gains kinetic energy and angular momentum from its interaction with that rotating cylinder. Very similar thing can happen when one of these axions flies by a rotating, spinning black hole. In this case, it's the event horizon of that black hole that provides a little bit of, quote, friction. And so this is spinning. That axion comes in. When it passes by that horizon, it gets a kick in energy. Essentially extracts a little bit of energy from that black hole and flies off. So, but it doesn't sort of fly off to infinity. It's effectively gravitationally bound to this to black hole. So what it effectively ends up doing is it's bouncing back and forth. Every time it passes by that black hole, it extracts a little bit more energy from it, bounces back here, extracts more energy, and just keeps doing this. And so what you ultimately end up getting is essentially this massive cloud of QCD, or really any axion, that's surrounding that black hole, essentially sapping it of its energy and causing it to stop spinning as rapidly as you would anticipate it to spin. And this actually gives us a way now of searching for these kinds of axions, because we can go out and do observations for black hole spins. So if we see a population of black holes that are spinning at a given frequency, then that means that axions must not have caused it to spin down. But if we're somehow not seeing black holes with particular spins, then that could be evidence for the presence of these massive axion clouds that are forming around these black holes and sapping them of their energy. So one of the constraints that's been very powerful from these black hole measurements is actually to sort of put a bound on that energy scale where you expect that that PQ symmetry breaking to occur, and it sort of puts it just below, in sort of this range just below what's called the Planck mass, which is an energy scale above which sort of regular physics, we can't explain anything anymore. All right, so with that backdrop, I just wanted to end this talk by talking a little bit about laboratory searches for dark matter. So we've been focusing a lot on what the presence of dark matter does on galactic scales, cosmic scales, but what if we actually want to detect some of these waves in our experiments here on Earth? There is a vast program that's seeking to do this, and the basic idea is as follows. What we're doing is essentially zooming in on this halo. So we exist here, right? We're the sun, we're Earth around sun, and rotating around in the disk. But we're essentially living in this massive dark matter halo. So those dark matter particles are flying through this room right now and flying through Earth. And so if we build a detector, we could hope to potentially detect some of these very weakly interacting particles that are essentially bathing us and from this massive halo that surrounds us. We already have some sense, based off of properties of stars near the sun, of how much dark matter should roughly be near us. Like the estimate is that the number density of these axions goes as about 10 to the 14 axions per centimeter cubed. That's if the mass is about 10 to minus 6 eV. These are huge numbers. So that means, like, in this room right now, if we take a cubic centimeter, we'd expect to see 10 to the 14 of these axions in that cubic centimeter space. The reason we never actually observe them or note them now as we're sitting here is that they're so incredibly weakly interacting that we can't detect them yet. But if we can sort of strategically build something that is sensitive to these kinds of particles, then we might have a shot of being able to actually kind of snag one of these and study them in a lab setting. So there's a variety of ways in which we can search for the kinds of experimental signals that these axions would leave. One effect is that it would cause spins in your detector to precess or kind of rotate around a little bit. So these axions essentially act as sort of anomalous magnetic fields. And in the presence of the axions, let's say a neutron spin would rotate around like this. So if you build an experiment that is sensitive to the direction of a neutron spin and you sort of observe it very closely to see if there's this kind of periodic motion to it, that's one way that you could potentially end up detecting the presence of this axion field. And this was just one example of this was work that was done at Princeton, led by my experimental colleague, Mike Romalis, who had built an experiment essentially in the basement of our physics building that had a bunch of these, it was a glass cell that had potassium and helium-3 in it. And the helium-3 would be interacting with the axion in this way, so through the neutron. So if there was an axion present, these helium-3 spins would start kind of precessing like this. And there are, once the helium-3 starts spinning, then that causes the potassium to start spinning a little bit. And then you probe the spin of the potassium and measure that out. So this was data that my colleague, Professor Romalis, had that we were able to go in and see if we could search for some of these signatures. Another potentially great way, and actually there's so many different experiments that are built around this particular interaction for detecting dark matter axions, is the interaction of the axion with light or photons. And the neat thing about this is that it allows you to use really powerful magnetic fields to essentially convert axions to light or vice versa. So essentially a magnetic field is a collection of what we call virtual photons because we can't actually observe them. And so if you sit your very powerful magnet somewhere, then you have the axion that can interact with those virtual photons and converting them to a photon that we can actually observe. So if we, in this room, put a very powerful magnet, then we might hope that an axion flying through could sort of trigger the production of this very sharp light that would come out of it. And this is essentially the basic premise behind one of the sort of really pioneering axion searches that's referred collaboration that's at ADMX. It's based out in Washington, University of Washington. It's literally that idea. So they have this sort of very powerful magnetic field. They're waiting for an axion to fly through, hoping that then it ends up converting to a photon, which that they can then record. But in order to enhance the signal, they put all of this inside of a resonant cavity that essentially enhances the signal from the photon that's produced. And this here is actually a picture of the cavity, so you kind of get a sense of the scale of the experiment. So that big cylinder there is essentially this cavity here that you're seeing in this diagram. A separate and related approach is to use axions that are produced in the sun. You can have these sort of photon-photon interactions in the sun that produce the axions. Those axions would travel towards us, and then we'd have a detector on Earth, again, a very powerful magnetic field that converts the axion to an X-ray, which we would then end up detecting. And so this approach is well underway in an experiment called CAST that's built at CERN. And here you can see, I believe this is the magnet up here in blue. So before concluding, I just kind of wanted to give you a sense of the region of parameter space that we've probed so far and where we hope to cover in the next decade or so. And it's summarized, it's a somewhat technical plot, but the x-axis here is the axion mass, and the y-axis here is the coupling between the axion and light. So as you move down in this direction, you're moving to axions that couple more and more weakly to light. And all of the regions here that are colored are regions of this space that have been excluded by searches that have been done so far. And the two that I highlighted earlier, so that CAST experiment, which is looking for axions from the sun, they've excluded this range up here. And that ADMX experiment based out of Washington has excluded this range in here. This yellow band is sort of a really key target. So the QCD axion that we talked about previously lives in this regime here, right along this yellow band. So if we want to really kind of be probing that very well-motivated region of wave-like dark matter, we need experiments that are essentially can reach sensitivities that they cover that band. And you can see that right now, there's only a small subset that do. But there's been an incredible amount of activity in this direction and a lot of really good ideas. And these light-shaded areas are where there are current proposals for experimental approaches, either being built or about to be built, or trying to get funding. And what's really heartening to see is that a lot of these essentially end up covering almost the entirety of that range. So we are in a point in time where we're really going to be, over the next decade or more, we have the technology to be able to search for these kinds of wave-like dark matter particles here on Earth and really test some of the most well-motivated candidates in this regime to answer some of these sort of key questions in particle physics. So with that, I'll conclude. And just to summarize, dark matter remains one of the biggest questions in physics, and it's a challenging problem because there's such a wide range of particle masses that can explain the dark matter, and each of those mass ranges sort of yields very different kinds of observational consequences and also the kinds of experiments that you'd want to build. Wave-like dark matter is a particularly interesting and exciting angle on this. As we've seen, when you can make the dark matter ultralight, that essentially ends up making macroscopic, you think of that as a wave with a macroscopic wavelength. Sometimes those wavelengths can be as large as galaxies, and so this leads to these kinds of interference patterns on these galactic scales. So wave-like dark matter, gives us these spectacular signals both in the cosmos. We talked about the signals that we see in galaxies, early galaxies, black holes, so forth, and then also in the lab. Given the quantity of data that's coming online, both observationally as well as with these proposed experiments, hopefully we'll be able to really kind of pin this down and discover this class of dark matter, should it exist, in the coming years. So I'll just end by acknowledging members of my group who are always helpful and contribute to work in so many different ways, and really kind of highlight Malta Bushman and Ani Prabhu, who are two postdocs who really doing a lot of work on this Axion front and who contributed in various ways in the preparation of this talk. And with that, I'll end, and I'm happy to take any questions. Thank you.